Right, well, thanks very much for the introduction and for inviting me to come along and talk about this sort of multifarious subject. Crude oil, the world wouldn't exist in the form that it does without it. Biodiversity, well, also that's something else that we need. And I will try and weave that in later. But first of all, I want to talk about the oil situation. It's probably the most important source of energy that we have. If you compare the use of oil to other sources, it's got the lion's share, basically. Coal is catching up to some extent, and gas, nuclear and hydro about 5% each, and renewable energy, basically solar and wind power, probably a couple of percent. So really, we're reliant on the fossil fuels for about 80% of the energy used by humans on Earth. This you might call the good old days. This is the Humphreys-Jones giant gusher, drilled out in Texas almost 100 years ago. And why do I call it the good old days? Because at that time, it was necessary only to expend about the amount of energy contained in a barrel of oil to recover maybe 100 or so barrels. Like investing £1, getting £100 back. Pretty good investment. But of course, things have got more difficult. We've used up a lot of the easily got oil, so the world average is probably below 20, not 100. Some of the US situation, it's probably about 10 or 11. Oil recovered from fracking in the sweet spots is of similar order, probably, in terms of energy return. But the very heavy oils are probably below 5. So it's becoming harder and harder to maintain the oil flow into world civilization. We produce something like 30 billion barrels of oil every year, which is absolutely amazing. I can't imagine what 30 billion barrels of oil or 30 billion anything is, but it works out to about 84 million barrels a day, depending on exactly what you count as oil. So that's about 1,000 barrels a second. So every second, we get through 1,000 barrels of oil. The major producers are Saudi Arabia and Russia, and between them, they produce something like a quarter of the world's oil supply. Crude oil is a very various material. Light oils are very freely flowing. Heavy oils, well, the very heavy ones can be like the black stuff on the road outside. Sweet oils, they're easiest to handle. They're low in sulfur. Sour oils are 2% and above in sulfur. They're much more difficult to deal with. Lots of light sweet oil, which is easiest to refine into petrol in the Middle East, basically, and other places, but the Middle East certainly is holding quite a bit of it. This is an exhibit from the Norwegian Museum of Science and Technology in Oslo, and basically it makes the point that oil, as I say, is a very various material. Some of the samples are dark in color, some lighter, some are freely flowing, some not, and they contain different molecules. And you don't really have to drill so far apart in terms of distance in an oil field to sometimes recover quite different material with different properties. So the big question is how much of the oil is remaining across the world. A lot of the oil that is left contains a lot of sulfur, and it's heavy. For example, from the Orinoco belt in Venezuela, it takes a lot of costly processing. And sometimes when it is claimed, for example, there is supposed to be 500 billion barrels of oil to be recovered in shale. Well, maybe only 2 or 3% of that will actually prove recoverable. It's a difficult thing. This is the difference between a resource and a reserve. The resource is basically what's in place or might be in place. The reserve is what can be technically but also economically covered. It's also sometimes said that America has 2 or 3 trillion barrels of oil in the form of oil shale. But this actually isn't oil at all as we know it. It's kerogen. Kerogen is immature oil. Basically, if it had been put by geology in hotter regions of the ground, it would have been cooked into something that we know as crude oil. But if you want to convert it into oil, you've got to heat it up. That's quite a high energy process, so the energy returns are correspondingly less. So we need oil to fuel the whole of the world's transportation, pretty much, but it's also the raw carbon feedstock for all plastics, pharmaceuticals. Really, the whole world runs on it. But also, without oil and natural gas to make fertilizers, modern agriculture couldn't exist in the form that we know it. And Basically, you need oil to fuel the tractors and the combine harvesters and so forth to grow this stuff. But food isn't consumed where it's grown by and large. It's going to be moved around nations and around the entire world. This is a bit of a poster child, actually, because for the unsustainability of agriculture. This is a field of soybeans growing in Brazil. And at one time, this field was actually rainforest. So this has been cleared. And of course, the mighty array of machines run on diesel refined from crude oil. But the dust that's being thrown up behind them, that actually is the topsoil. And so this is prone to erosion. And this is one of the major problems that we have in maintaining agriculture into the future. 98 oil-producing countries can be identified, certainly on this chart. Well, those in red are past their peak at oil production. And it's reckoned that the conventional oil supplies are declining by about 4 or 5% per year. And what that translates to is that we need to find a new Saudi Arabia's worth of production every 3 or 4 years. And that is got from unconventional oil. It's got now from fracking, it's got from processing bitumen, drilling in deeper and deeper water. But as I was identifying earlier, we have to work harder and harder to maintain the flow of oil into civilization. This was put together by the energy, they're basically part of the American energy, Department of Energy, actually, and the Energy Information Administration, that's right. So they're not some crank environmental group, but their prediction is along the lines of what I've said, that we are losing a supply of oil which has to be filled to maintain and even grow the amount of oil that comes as an energy source into civilization. So this is the sister Paris-based agency, the International Energy Agency. This is their world outlook for 2012. Things haven't changed tremendously since then, but they have at least, rather than claiming unidentified projects, they've made a stab and an estimate at where the new oil is going to come from. So the dark blue bars at the bottom, that is currently producing, if you like, regular oil. That peaked in about 2005 or so. But what they're reckoning is that that will be made up by fields yet to be developed. So that's the light blue line above. Now, mostly those will be fields. They know where they are. A lot of them will be in deep water. But it's not worth producing from them until the price of a barrel of oil goes up to 100, 150 or what. And with the crash in the oil price recently, this has actually basically caused a withdrawal in investment from various kinds of unconventional projects. So I think the price has to go back up again if we're going to maintain the oil supply. Fields yet to be found, yes, okay, similar sort of thing. Natural gas liquids, they're not exactly regular petroleum, but they can be used for different purposes. And really, the light tight oil, that is oil recovered from fracking, shale mostly, and really that is not going to make a huge contribution. It's significant, but it's not going to be huge. So the alternatives to oil. If we need to look at some point, and we do, at a society that doesn't have the level of oil flowing into it that it has now, then what are we going to do instead? Because we are so dependent on it for everything we use. So we need to find alternative fuels and indeed carbon feedstocks for industry. The other argument, of course, with all the fossil fuels is burning them contributes carbon dioxide, so that contributes to the global CO2 budget. And so you've got the climate change aspect. Some people argue, well, okay, isn't this a good thing? If we can't maintain our oil supply, wonderful, our CO2 emissions are going to fall. But of course, we have this complex civilization entirely dependent on moving people and goods around. And without oil, this would prove a rather challenging thing to do. Now, people talk about biofuels quite a lot. So this is a field of sugar beet growing in Norfolk. Grows very well in this country, rather like sugar cane grows in Brazil, for example, which is a huge bioethanol industry. But okay, so if you grew your sugar beet and you get sugar out of it and then ferment it into ethanol, you might get something like 5 tons per hectare. Now, if we were going to provide our liquid fuels for the UK in terms of bioethanol, we would need somewhere more than twice the amount of arable land that we have. So to put it another way, if we stopped growing food and we went over to growing sugar crops, then we could maybe only produce about 45% of our liquid fuels in this way. There's also a lot of hope for cellulosic ethanol, and this is not quite at the level of commercial production, but for example, people talk about growing miscanthus. And the good thing about this is that you could grow the stuff on marginal land. You don't need to use arable land. So that's going to be good. But still, the yield is about the same, really about that 5 tons per hectare. So really, you're going to need a hell of a lot of land to actually start to produce ethanol, cellulosic ethanol too, from this kind of technology on the level that we get liquid fuels out of petroleum. And there are difficulties. The enzymes that are used to degrade the cellulose into sugars, they're expensive. And again, I think there are considerable limitations. Biodiesel is somewhat worse in terms of overall yield. Rapeseed gives not 5, but maybe 1 ton of biodiesel. And assuming that we converted all the engines in this country to run on diesel, because you get more miles per gallon, if you like, out of diesel engines than you do from petrol burning in spark ignition engines, you would still only be able to provide maybe 1/7, 14% of that fuel requirement. The other thing that often doesn't get a mention when people talk about biofuels is that if they're produced from land-based crops, well, basically they have to be farmed and harvested in the same way. So you're still needing those oil-powered tractors and combine harvesters to do this, along with large quantities of fresh water. So in a way, you're kind of substituting one problem by another. You're maybe producing liquid fuels, but you still need, given the machinery we have, fuels like diesel refined from petroleum to actually run the whole show. Now, this might not look like the most prepossessing material, but there is a lot of hope, in fact, in some quarters, that we don't need land-based crops. What we can do instead is to grow algae and process this into biodiesel. It's a good idea in many respects, as I will attempt to indicate. Now, the algae, they are green because they contain chlorophyll, so they undergo photosynthesis rather like land-based crops. So the idea is you grow the algae, they absorb CO2 from the atmosphere, and then having dried this stuff out, you can then process it into some sort of biofuel. Good idea. Now, some of the good aspects of this, for example, is that you get a much higher yield under the best conditions, at least, maybe 100 tons per hectare, actually somewhere between about 40 and 100. So if you wanted to make that 40 million tons of biofuel, you'd only need a few percent of the total UK land area. The other thing, of course, if you could fabricate these tanks, you could stick them anywhere you like. There's a project going at Cranfield University where they're considering floating the tanks out at sea. It'd be a very interesting feat of engineering to do this, but of course the idea is you're not compromising land at all that could be used for food production. Algae, depending on the strain, it grows quite well on saline water or wastewater, so you don't have the same demand on fresh water that you do with the standard biofuel crops. What I really like about this idea is, although I don't think we're going to get 30 billion barrels a year's worth of algal fuel, you can use this in a sort of integrated strategy. So, okay, we've got a problem, we don't want to pump CO2 into the atmosphere. If we could capture that and do something good with it, that would be good. We also have issues from agricultural runoff, for example, of nitrate and phosphate getting into the water systems, causing algal blooms, dead zones, and all of this via eutrophication. So the idea is that you basically feed these things to your algae. And this is the idea. I hasten to add that this is an artist's impression. Nobody's actually produced this, although In 1973, when it was the first of the oil shocks, this was the time when the mostly Middle Eastern oil-producing nations gave a show of strength against the West for their support of Israel over the Yom Kippur War. They pulled back the production or the export of oil by 5%. The price went up around 400%. So that was a clue as to how vulnerable the West was at that time on foreign oil exporting nations. So they had about a tenth of a hectare, I think, that they grew these algal tanks on. But the idea, you can see, these tanks are full of green algae, and if you had that built next door to a power plant pumping out CO2 fired by coal or gas, and you also had it next door to a sewage treatment plant, a wastewater treatment plant, you could basically integrate the whole thing. So you get rid of two problems that are costly and difficult and undesirable, and basically you grow the algae, and then you process the algae into a sort of crude oil liquid fuel substitute. I like the idea. As I say, I don't believe it's going to really solve all our problems, but it's a kind of environmental cleanup strategy combined with a potential energy producing source. I think on a local scale, it could actually be quite useful. Okay, fracking. I want to say a few words about this because fracking, really hydraulic fracturing, is the way I see it, yet another way of trying to fill the gap in the decline in existing petroleum crude oil production. Now that's a picture of a fracking site, and it's been described as being a bit like the circus coming to town because you have all these lorries and you've got all this stuff to bring along. Of course, eventually the circus leaves town, just leaving the wellhead, but there is a fairly exciting period where a lot of stuff is moved in and then moved out and things happen in between. Now the process itself, basically this sort of outlines some of the different elements. In some cases, you need to construct new roads. Of course, you do with many operations of various kinds. And you have to basically support the site against erosion control. You have to dig pits out for the drilling fluids, the drill cuttings, etc., etc., etc. And as I say, eventually it's got to be taken away again. And the wellhead is the thing that is left behind at the end of the day, probably after a couple of months or so when everything else has been done. And that is thought it may produce for perhaps 30 years into the future. Nobody knows because it's not really been done on the grand scale over the longer time. So the process itself, hydraulic fracturing, I mean, why bother to do it? Conventionally, it's not really done in this way. Drilling is done vertically mostly. Yes, there's directional drilling and so forth. But one of the key features, it's what's often described as horizontal drilling. Well, the reason for doing this is if you just drill down vertically, you only hit a given volume, basically, if you like, of shale in this case. But if you drill down and then at some point you mechanically turn the drill so that when you get into the shale, you're then drilling horizontally. Of course, you can access into hundreds, thousands of meters. So it's a very good technology. Different ways of doing this, I'm just describing it generally, but basically a pipe in segments is put down. Then typically a perforating gun, which is a device with very highly positioned high explosives, is detonated in that. That blows holes through the pipe and into the shale. Okay, so then the thing is set. It's often done in multi-stages. You can have up to about 30 of these stages in the more extensive ones. Then the fracking fluid is pumped down. That contains mostly water. It also contains sand, and if you can actually read that on the slide here. But basically the purpose of the sand is that once you've cracked the rock open, then these small grains actually hold the cracks open, because otherwise the pressure of the rock on top would probably close them up again. That would be the sort of gravitational tendency. And then once you've done this, then basically the oil or the gas can then be brought up to the surface and then it's taken off to the market. That, in a nutshell, is the process itself. It takes a lot of volume, if you like, fairly large quantities of water, chemicals. Most of the chemicals that are used in fracking are not toxic particularly, but it's not these days for sure, and I think the industry is certainly looking to this aspect that they're not. But the pressure can be pretty high, up to about 1,000 times atmospheric pressure, and then when the rock cracks open, well then the pressure is dropped and then you can carry on doing the job. I mean, people are concerned about these various aspects because a single well can produce several million gallons of wastewater, and people are concerned about what you put down in the first place. As I say, most of the chemicals put in fracking fluids are not particularly toxic, but people are also concerned about what might be washed out of the shale that had been locked up there over millennia, like radon, for example. Another point is that shale gas or shale oil wells tend to deplete relatively rapidly, so after a couple of years maybe, you've only got 20% of the original production coming out, so you've got to drill, baby, drill. You've got to keep drilling to maintain the overall output, basically. And it's been estimated that worldwide, if we're really going to go for it, in Europe and elsewhere, we'll need to drill over 1 million new shale gas wells over the next 20 years, which is a huge investment. It's not cheap technology. It's not as cheap as it was just drilling holes in the ground in the old days. Right, so there are these various concerns that the process can contaminate groundwater, air and so forth, and I don't really know what the answer is because I've heard some terrible stories, but the scientific data that I'm aware of would not substantiate that anything terribly bad has happened from a fracking operation so far. There are stories where the fracking fluids at surface level were dumped and so forth in the past, and I think that might be part of it. But in my opinion, I think it's necessary to do a detailed chemical analysis of the groundwater, the soil, the air, before you start, when you start, and then basically over the next 30 years that these wells are going to produce for. Then that way you will know the answer, because otherwise I think there's a certain amount of speculation. President Obama has said a couple of times that America has enough gas for 100 years. Well, okay, I think that's the difference between a resource and a reserve. If you add up everything optimistically, you come to about 90 years, but the proved reserves are something like 12 years or so. I'm not saying there won't be more, of course there will be, but it's probably not quite as good as might be hoped. Okay, the US is the only place where fracking has been done seriously and successfully. We're looking at it in Europe. The only other place we can really look at outside of the US is Poland. To the best of my knowledge, 66 wells were drilled in Poland, and only one of them came out with an approximately commercially good production rate, because the geology is different, the rocks are different. So it's not necessarily going to be the case that we'll be so lucky, if you can use that word, in Europe as they have been in the US. There's an interesting article published in Nature which airs some of these things, and from people I've talked to, as I said earlier, the energy return on energy invested for example, the Bakken is supposed to be about 12 to 1, something like that. But some of the other spots they've tried drilling in are much less than that. So it's an unknown quantity. Shale gas contains methane, that's the principal component, also lighter, slightly heavier, but also light hydrocarbons, heavier ones too, but ethane is another one. But they can also contain nitrogen, hydrogen sulfide, carbon dioxide. A chap I was talking to, a Russian geologist, was referring to the Polish situation, and he reckoned that out of some of the wells they drilled in, the gas that came up was so full of nitrogen, you could hardly burn it. So you don't know what you're going to get until you actually start drilling in terms of production rate or quality. The Royal Society came out with a report some years ago, and they reckoned that we could do hydraulic fracturing safely in the UK, but as they say, only so long as it's strongly regulated. Another difference between the US and Europe, are you familiar with the term Mamberland? It means miles and miles of bugger all. Right. Well, what that refers to is that in America and Australia, for example, very many operations, they are done in wide open spaces where few people live. Of course, this is a highly densely populated island, so people are also concerned that if fracking is done, it's going to be done underneath their houses, effectively. It's also different that if something is found underneath your property, in America, well, you kind of own it. You're going to earn some money for it. But in this country, the legalities are not necessarily that way. But it is true that shale in general produces more gas than oil. And so my point is that if what we're trying to do is to preserve the overall flow of oil into civilization, fracking is probably not, or not in the longer run, going to completely solve the problem. It may buy time, but again, none of these things are the total solution. Okay, so at some point, saying we're not going to run out of oil anytime soon, but it's maintaining the production rate that's the difficulty. And having to do that from more difficult materials, more expensive, more energy consuming to produce them, etc., etc. We are sort of running out of the good days, if you like. So, really where I start sort of alluding to biodiversity. The UN General Assembly declared this year the International Year of Soils. This is their manifesto, their mission statement. Without going through all this and reading it all out, the point here is to try and make everybody, everybody possible as aware as possible of just how important soil is in terms of growing food, basically climate change adaptation and mitigation. This is largely the role of the soils in the carbon and the hydrologic, the water cycles. So soil is pretty important stuff, and we are degrading it. So this is really what this is about, to try and get this message around, and especially to decision makers, whoever they may be, who may be able to do something about not treating the soil like dirt, as it's been described. The principal cause of soil degradation is erosion, but of course there are many other facets. Compaction is a big problem, chemical contamination and so forth, and various things that basically destroy the biodiversity, the life in the soil food web, it's been described as. It's a global problem. Very degraded soil, stable soil. Well, there are various definitions for these things, but very degraded soil has been described to me as land that has lost something like 70% of its topsoil. So that's significant. But you can see that there is degradation across the earth, basically. So what I find really quite amazing is that 1/4 of all the Earth's biodiversity is reckoned to be in the soil. That's to say 1/4 of all the living organisms on Earth are in the soil. Mostly those will be bacteria, because that is really the great home of bacteria, and they are incredibly biodiverse, able to evolve in different forms under different conditions. But really you've got this whole sort of litany of bad statistics. Half the land used for agriculture is reckoned to be degraded moderately to severely, mostly by erosion. It takes, depending on the conditions where it is, it can take a couple of 100 years to maybe 1,000 years or more or less to form just an inch of soil. But soil on agricultural land is being lost at a much higher rate than that. This is a big problem. In the last 40 years, we've lost something like 1/3 of the world's cropland, or at least it's become unproductive, and quite a lot of it has been abandoned as a result of soil degradation. And the concern, of course, is that if the climate changes, then this is likely to have a rather more sort of scourging impact on the world's food production systems, and it's reckoned that about 50% of the world's livestock are vulnerable to degradation exacerbated by climate change. And yet, we need apparently to produce 70% more food by 2050, not only to feed the growing population, but a more affluent population who consume more meat. Interesting sort of demographic change, perhaps. But anyway, the poor old soil is really having a lot of pressure put on it. This is a connection that you're probably well aware of it, but people aren't necessarily. This is the connection between soil and water. Basically, soil is an implicit part of the hydrologic cycle. So water evaporates from the seas and lakes and surfaces and so on. rains down. What you really want it to do is to be absorbed by the soil. The soil, good healthy soil with good structure, and if it's covered, should act like a sponge. So it absorbs the water, it infiltrates into it, and this recharges the aquifers and the groundwater systems. If you don't do that, if the soil loses its structure, and if it becomes compacted, then you get more of the water actually running off the surface, which contributes to erosion. And if you're not recharging the groundwater systems, then this contributes to droughts. So if you can get the thing back into balance, you get the water and the soil where it should be, and not where you really don't want it to be, where it causes all kinds of difficulties. The critical factor, actually, in protecting soil from erosion is to cover the ground. And this is an interesting paper, which indicates that if you have about 20% coverage, the soil is eroded at a rate of something like an inch in 25 years. If you cover the ground to the extent of about 80%, you reduce that by a factor of 10. So it takes 250 years. And that kind of brings it back into the sort of natural balance, the rate at which soil is eroded and is formed in the first place. So this seems to be quite a critical feature, definitely. Okay, ways to protect and generate soil. Plant trees is one thing, reforestation. Once upon a time, I could never understand why all these green people wanted to go around planting trees. I couldn't quite understand what this was about. But I realized trees are actually pretty wonderful things. The root systems, they contribute to the soil food web. If you have a living forest, you have a communication within the soil between everything that grows there, mostly through the mycorrhizal mycelium that forms a kind of holistic connection with the root systems. But you can plant all kinds of things, cover crops, peas and beans, they're nitrogen fixers, that's good. No-till farming, there's a lot of work on that. Some people swear that this is a much better way because you're not physically breaking up the fungi in the soil. This helps to build the soil organic matter, and really so on. 5 million hectares of barren land have been brought back to life in Niger at a rate of a density of about 40 trees per hectare. Basically, this is large-scale pruning. You basically prune away anything that's stopping the trees from planting, and you let them do what they want to do, basically. Well, the whole lot. But if you have good soil, what you've done is to rebuild the soil food web. It's reckoned that in a teaspoonful of good soil, you've got something like 1 billion microbes. Amazing. And millions of different species. We don't really know them or understand them, but it is a hugely vibrant ecosystem. And if you have that working, then you have a fertile soil that recycles nutrients and does all sorts of good stuff. So this is a picture of the soil food web. You've got the different trophic levels. Basically, you've got the simple ones, the single-cell creatures, the bacteria, the fungi, and so on. And basically, you have a recycling of nutrients as these different species consume one another and the excretion products and so on. But a good way of telling that your soil food web is working, you don't need a microscope. If it's full of earthworms, like a good compost heap, then you can get a good judgment that everything else is in place. Interesting headline here from The Independent. They're not usually too bad. It's not the Daily Mail. Anyway, they're saying that Britain has only 100 harvests left in its farm soil. Anyway, I contacted the people they were quoting from Sheffield University. And I said, did you really say this? And they said, well, no, we didn't actually. But the point was, that was basically a journalist kind of summarizing what they'd said. Their point was that large-scale agriculture is denuding the soils of nutrients and destroying the organic matter and the soil structure. And they reckon that it's going to be sometime this century we're going to have some issue with soil fertility. But what they find is that if you look at allotments which are tended by people on a small scale rather than industrialized agriculture, they tend to be much richer soils. They hold on to their nutrients, they've got better structure, etc., etc. And the conclusion is that actually we should start to use urban space to grow stuff in. that this might be a more sustainable way of going forward. And the other issue, of course, is that there has been, as the headline says, a sharp decrease in biodiversity. And the more biodiverse a system is, the more resilient it tends to be. And I think it probably goes in the contrary. Okay, so if we were going to go around and start producing stuff on the small scale, what might be a good way of doing this? Allotments, people have had allotments for a long, long time. Dig for Victory in World War II produced a huge amount of the food for this country. But another thing, another approach that I would like to raise mention of is permaculture. Who's familiar with permaculture? Who's heard of it? Right. Okay, well, that's a darn sight better than most audiences, actually, because most people I know, you mention permaculture, they don't know what I'm talking about. They've never heard of it. Okay, well, for the benefit of those who are not so familiar with it, permaculture, basically it was invented by a couple of Australians, so it's said, about 40 years ago. It's a portmanteau word for permanent culture, permanent agriculture. The value added with permaculture is it's regenerative. It's not just sustainable. Sustainable means you can carry on doing the same thing in perpetuity, which is not bad. But if you've got something that's regenerative, then you can use the method for restoring degraded landscapes, for example. And there are some fantastic projects around the world. In Africa, for example, the Chikukwa project in Zimbabwe, where a highly degraded, eroded landscape has been brought back to verdancy over about 20 years by applying these permaculture agroecological procedures. Well, Einstein apparently said, I never know whether these quotes are true or not, but he apparently said, you cannot solve a problem from the same consciousness that created it. You must learn to see the world anew. And that's a bit like permaculture, because permaculture doesn't focus on the individual elements, be they plants or other inputs or whatever else you have. Basically, it's about the whole picture. It's about the final design, and you put the elements together so they reinforce each other and they work holistically. That's another word I don't like using particularly, but anyway, they work in a sort of integrated fashion. So a few things I note there: companion planting, no-till, building soil structure. Basically, if you have a good system with good soil, it holds on to the water and the nutrients better, so that cuts down the amount you need. And also, permaculture exploits the third dimension. And I'll show you in a second a sort of schematic of a food forest, basically, where you put together different plants that grow at different heights, therefore have different root depths. So you're sampling the different photosynthetic availability of light, but you're also sampling the nutrients in the soil differently. A good example, this is what's called three sisters planting. So you grow a bean and a corn and a squash. So the bean fixes nitrogen, very good, by its roots. It grows up the corn stalk, and you have a squash there, which benefits from the nitrogen, but its broad leaves also shield the soil and help with the water retention. This is what I kind of like by a permaculturist. One of the central features of permaculture is the problem is the solution. You don't actually have a problem in the ideal world. Okay, so this example is if you have a garden or some plot that's overrun with slugs that are eating your crops, well, you don't have too many slugs, you've got too few ducks. So the solution is that you bring the ducks in. The ducks eat the slugs, and of course they provide eggs, and so on and so on. So it's kind of integrated thinking. So I'm not going to go into this in any great detail, but as I say, permaculture isn't a sort of entity or a thing, it's a design system. These are the 12 principles of David Holmgren, who was one of the originators of it. I mean, permaculture rests on principles that were known a long time before that, but you can see things like produce no waste. Well, nothing in nature, in a forest, for example, goes to waste. And the three principles, the ethics rather, care for the earth. Yep, okay, you don't want to degrade your soil or anything else. You don't want to degrade people. And fair shares, that's very often taken to mean don't take more than you need. But more importantly, it's about returning surplus to an ecosystem. So it actually nourishes the whole thing. And it doesn't make a lot of sense when you first see this, or it didn't to me, but when you start to get involved with it, then suddenly the penny drops. So here's a forest garden. This is the principle of layers. Okay, you've got a canopy, a very large fruit tree, say, and you can arrange all these other things that, as I say, grow to different heights. Therefore, some of them are shading others are getting the full benefit of all the light there is, but the roots are growing at different depths, etc., etc. Some plants, like borage, for example, have very, very deep roots, others less. So you really are exploiting the third dimension. So that is the beauty of this kind of integrated way of doing things. And if you think, well, does this actually work in practice? Let me show you this. Okay. This is the RISC roof garden. It's quite famous in Reading. It's quite famous in permaculture circles. That's the Reading International Solidarity Centre, which sounds a bit subversive. I suppose it is slightly. You certainly get people there who care about what's happening to the earth and so on. And there's a lot of good stuff goes on there. But in addition to that, it looks like a jungle, doesn't it? But this is actually growing trees and all in a foot of soil on a building in Reading Town Centre. There's more than 200 different plants there and umpteen different species. And, for example, there's a huge cherry tree, which is about 20 feet high, so in a foot of soil, its roots are spread out pretty dramatically, you can imagine. But I've been up there many, many times, but the roots are so sort of they fill the soil sufficiently. You can't get a spade down there. It's absolutely solid, basically. But there are trees, there are shrubs, there are all kinds of different things. So if you can do that on top of a building in Reading with permaculture, then I think you can do all kinds of things. And it was, among other things, developed to show what might be done with urban space, because people have been thinking for a long while that we could actually grow a lot of what we need actually within the urban environment. Well, I'm trying to sort of summarize things here. Okay, biodiversity. Yeah, some people are concerned that the world population is too big. Carbon emissions. What else have we got? Declining peak resources, whether that be fossil fuels, water, because we're pumping aquifers in America, in the Middle East, and elsewhere. Peak phosphorus. We've actually got a peaking in fish stocks. It's a bit alarming. We've actually got a peaking, apparently, in the amount of good land with good soil, basically, uranium. And it is reckoned we are now in the midst of the sixth mass extinction, because the loss of biodiversity is now at as great a rate or more than it is reckoned to have been in the previous 5. So this is quite significant. There are all sorts of other issues, basically, that people tend to focus on and say, we've got too much of this is the problem, this is the problem. I look at it a bit differently. I don't think these are individual problems, but rather they are symptoms of a single problem, and that's that we're using up our resources too quickly. And we're not considering recycling or regenerating soil, preserving water, etc., etc. Somebody described this, not by me, I forget whom, anyway, as the sins of the fathers, because it's a kind of, impoverishing process where we exhaust our resources. But unfortunately, we also create in the process carbon dioxide and so forth, which is causing other difficulties. And it is thought by various groups, including the transition towns particularly, that if we focus on the local scale to a greater extent, then we can become more resilient, rather in terms of our resources, rather than simply using them up and creating these problems. It's thought that if we were to use urban space, we could produce something like a third of all the vegetables that we need in this country, for example. Interesting thought. That's exactly what they did in Cuba when communism collapsed, and they didn't get the supplies of fuel, pesticides, and so forth, but they actually held the country together. Only 3.5 million people, but they actually used permaculture and agroecology, and they fed everybody. It's described as the special period, or the special period during peacetime. It's reckoned, mind, that your average Cuban lost about 20 pounds in weight during this period, but they did survive, and they produced more doctors per 100,000 than any other country in the world, so they held their education together. And permaculture certainly I think needs to be investigated in more detail because it does offer certain advantages, and if that's true, then we really need to look into that. And it seems to be true from many studies that if systems are more diverse, they're more resilient to water stress. That's to say, the Rhodes Institute in America, for 30 years they grew 2 plots. One is more conventional agriculture, the other is more organic. And they found that there's not a substantially lower yield from the organic compared to the conventional. Conventional, that's only been going on for 60 years or so, but you know what I mean, sort of more industrial farming. What they found was the organic systems that they developed were more resilient and the yields were better in times of water stress. And I know somebody called Ian Tolhurst, who's a sort of pioneering British organic farmer. He's going to have a celebration next year because he's farmed organically for 40 years. Good for him. What he found is that with his soils, that whereas in other places with the heavy flooding, the life was kind of extinguished, he was able to actually bring his fields back into production. So he's just got better structure, probably more oxygen in the soil. It's just a better kind of scene altogether. And they do tend, polyculture systems tend to be overall more productive than monoculture. Now this amuses me. Loss of biodiversity. Okay, this is a bit of an example, a metaphor for the modern age perhaps. You've got this chap looking over the garden wall at his neighbour and his very messy garden. He's got all this stuff growing there and he and his kids are having this messy time doing what they're doing. And he's paved his driveway over and he says, you should concrete over. It makes life so much easier. And well, in a sense it does, I suppose, if you don't want to do all these other things. But actually the fact that we've concreted and tarmacked over so much of the ground, this contributes rather significantly and badly to basically runoff and flooding. And indeed, it prevents or retards the aquifers and the groundwater from recharging. Right, in terms of carbon emission, I'm losing my voice a bit, I've got a bit of a cold, but I should be able to carry on for a bit. Very interesting paper in Nature, a sort of a mathematical analysis, which concluded that if we want to stand a 50% chance, that can be described as like playing Russian roulette with half the chambers empty or half the chambers full, depending on how you look at it. A 50% chance to avoid the mean global temperature increasing above 2 degrees by 2100. We need to leave a third of the world's oil reserves, half of its gas reserves, and 80% of coal reserves in the ground, up to 2050. And they say that the development of resources in the Arctic and any increase in unconventional oil production, what they're talking about there is kerogen from oil shale, particularly, are incommensurate with efforts to limit the temperature below 2 degrees throughout the rest of this century. In other words, we've got enough already. If we burn that, that's probably going to take us up above where we need to be. I think more in terms of production rates than static reckonings. And so taking their data and look at it in terms of production rate, you need to reduce the production rate of oil by about 5%. The gas supply, you need to grow by about 60%, and mostly it's about the substitution of gas for coal, because gas produces less CO2 per unit of energy. And they reckon that if you take that mix, you could reduce the CO2 emissions from 48 billion tons of CO2 equivalent in 2010 to less than half that, a drop in CO2 emissions of the best part of 60%. And yet, if you look at the BP Statistical Review of World Energy 2014, which probably is more realistic in terms of what we're actually doing, although that talks about a substitution to some degree of gas for coal, the conclusion is that our CO2 emissions by 2035 will be up by 30%. So it seems that what we're doing is going rather in the diametrically opposite direction from what we need to do if we're not going to cook the planet. The future of energy. Well, I sort of come up with these, I offer you these few things. I think the most critical thing we could do is to look toward energy efficiency. So, for example, retrofitting existing building stock. Okay, we've got all these buildings, maybe 40%, or I don't know exactly, perhaps it's 50% of the world's population lives in cities, or it's going to be that way. We can't knock this whole lot and start again. So build super efficient buildings. So what we've got to do is to retrospectively insulate, for example, the building stock that we have. How much low carbon energy, how much solar and wind can we have? Well, we're only producing 2% of our total energy from these sources at the moment, so there are probably limitations, certainly against the time scale that we have, certainly with the likely decline in oil production. Some people therefore say, well, nuclear power is a good idea because it doesn't produce so much carbon dioxide. And people talk also about thorium molten salt reactors, liquid fluoride reactors, which run on thorium, not uranium. But that's the reason for talking about this. I think we will need to reduce our oil-fueled transport over the next decades and produce more of what we need at the local level. But also, all the energy sources are very thirsty. For example, if you're going to produce oil from bitumen, from tar sands, it takes, depending, 2 to 4 barrels of water for every barrel of oil. All energy sources, certainly hydrocarbons, take water to extract them. And it's reckoned that if we wish to expand our use of energy to the level that is anticipated by 2035, we will need to grow our use of water by 85%. And it might be this, because the world is water stressed. As I say, the overpumping of aquifers, for example. It could be the availability of water that limits how much energy we can produce. And we have, as I alluded to, also a nexus between water and soil in terms of the hydrologic cycle. So it's important for this reason too, to rebuild and protect the soil. And really, to sum it up, you can't decouple our use of energy from how we use water and soil. And really what we need to aim for is basically a sort of an integrated, sustainable system that is actually going to allow us to thrive and survive. And for sure, we live in very interesting times, whether that's a curse or not. And a few publications, some of them by me, on these subjects, which I will give you the references for if you're at all interested. Okay, I'll stop there. Thank you for listening to me.